Hi folks, welcome to this video on assigning meaning to slope. So we've been doing a bunch of work with differential calculus on finding slope, but we haven't talked a lot about what it means in context. And actually we know the answer to that question from when we first ran into slope. Slope is a rate of change, and sometimes actually seeing the graph can help us understand what is going on with slope, and also looking at the units that are involved. So here's a cute little thing that people sometimes do. This during a thunderstorm, they'll count the number of seconds between when they see lightning and when they hear thunder. And a 3-second lag between when you see lightning and hear the thunder means that the flash is about a kilometer away. So if we were to make a little graph here, distance in meters, at 1,000 meters, it's going to take 3 seconds. And I think it makes sense to put time on the x-axis, though you don't have to. Okay. So there's a point here, 1,000. And then it says at 5 seconds, it's about a mile away. So a mile is about 1,600 meters, roughly. And these are approximate. So there are a couple of points. And if you have a couple of points, well, you can find slope between them. So the slope between them, you could think just about rise and run. Or we could say it's delta y over delta x, or y2 minus y1 all over x2 minus x1. Any way that you want to do it. So let's call this x1, y1, x2, y2. And just for fun, we'll find the slope between them. So that'll be 1,600 minus 1,000 all over 5 minus 3, or 600 over 2. Now, right now, that answer of 600 over 2, or if you reduce it down 300, it means absolutely nothing. But if we put down that this is meters and this is seconds, then all of a sudden we can give some meaning to this. So it means 600 meters per 2 seconds, or the slope is 300 meters per second. In other words, it's telling us the sound of the thunderclap, the sound is traveling at a rate of about 300 meters per second. Now again, these are just sort of little tricks that you use, but is that about the speed of sound? Yeah, it is. So when we just saw the numbers that meant nothing, when we put in those units, then that rate of change has meaning. It tells us about a velocity just by the fact that it's meters per second. Does it always have to be distance and time? No. Here's another example. The population of Smalton was 17,302 on January 1st, 1998. So let's make this the year on the x-axis, and the population, or number of people, is 17,302, okay, in 1998. And I could graph the other piece of information. In 2015, the population of Smalton was, I'm going to put a little break here so these don't have to be to scale, 13,791. Again, we could find the slope between those 2 points. So we could just go, okay, this is x1, y1. You can do it the other way around, y1 rather. X2, y2. You could also just find rise and run if you want. But we're finding the slope between these 2 points. So slope is going to be y2 minus y1 all over x2 minus x1. And if you'd switch the definitions of what's x1 and x2, you'd have no issue. You'd get the same answer. So I can work that out, and it'll be negative 3,511 over 17, or roughly about negative 207. That means nothing without the units. The units are, those numbers, they represent the number of people. And the 17 represents the number of years. So the slope is really about negative 207 people per year. And it's a rate of change. The population decreased at a rate, because slope is a rate of change, at a rate of 207 people per year over those 17 years. Now, let's see, how can we make this a little bit better? First of all, how do we know it's decreasing? Well, you can just look at the graph, but also the negative tells you that it's a decrease. The other thing we want to say here is that that's on average, because we don't actually know what happened at every moment. Maybe the population of Smalton did something wild. Maybe it had a big boom, and then it's in the middle of a big bust right now, and it's going down really fast. Or maybe it's the other way around. Maybe it went down, and it is kind of having a little bit of a resurgence now. We don't know what's happening by just looking at the average. The average kind of helps, but it doesn't tell us what's happening in the instant. So the good thing that we've done so far is that we've looked at slope and we've assigned some meaning. So we found slope of a secant, and we gave it meaning, which is better than just having slope be a number. The unfortunate thing is that we found average rates of change. Okay, so that's because we found secant slopes. To find instantaneous rates of change, we would have to use the tangent slope. And that means calculus. Now, if you think of these two examples, for the population of Smalton, that average rate of change caused an issue because we don't know what's happening right at 2015. The first one, though, it's probably not an issue because it's not like sound is going to wildly vary in how fast it travels through air on Earth. It's going to vary a little bit depending on things like humidity and temperature, but on the whole, not a big difference. So this data over here in example 1 was probably linear to begin with. Finding an average rate of change or a secant slope is fine on a line because slope's never changing on a line. On something that might be nonlinear, though, it does make a difference. So, we found the average rates of change. To find instantaneous rates of change, we must use the tangent slope unless our original data was linear, in which case it doesn't really matter. The slope of the secant and tangent are the same. To drill down a little further on this idea, I want to send you to one of my favorite videos on the internet. You can find the link in the video description below. I'm going to try and have it pop up on this video, though we will see whether I have that level of YouTube mastery. So head over to that video and then come on back here. In this video, Mason launches his guitar into the air, his strap locks fail or something, and it goes up and down, and its height is modeled roughly by this. I did my best to estimate it, so if you were to think about what's going on with Mason's guitar, over time, its height in the air, I mean, it starts at waist level on a stage that's already above ground level, so I'm saying it starts at 2 meters, and it goes up, and then, sadly, it goes down, and it hits the ground. Now, the first question that's asked here is to find and interpret the function at t equals 2. And this is really key, the interpret part. If we just get numbers, it's not that helpful. So let's put in 2 into this function. H is in meters, t is in seconds. So after 2 seconds, we get -5, 2 squared, plus 9 times 2, plus 2, which would be -20, plus 18, plus 2, where the height is 0. Okay? So when time is 2 seconds, the guitar has a height of 0. The guitar hits the ground. And after that moment, this model is no longer valid because it's not like the guitar drills into the earth. Guitar hits not hits the guitar, but hits the ground. All right, find and interpret the first derivative at t equals 2. I'm going to use the Leibniz notation for a derivative here. So that would be dh over dt, or dh by dt. And so we'll get negative 5 times 2t plus 9 times 1. Or I think a lot of people will just want to write right away negative 10t plus 9. Lovely. That's the derivative anywhere. Okay. At t equals 2, let's sub in 2 for t. dh by dt is going to be, or you can say h prime, but there are going to be reasons this is a little better, is going to be negative 11. So what can we say? At t equals 2, the guitar is traveling downward. And this is the last instant in which it's traveling downward. Traveling downward because the derivative is negative. At a rate of. So anytime we find a derivative, we're finding a rate of change. A slope is a rate of change. At a rate of 11 something. Now, here's the nice thing about the Leibniz notation. It tells you the units. Height is in meters per time, which is in seconds, at a rate of 11 meters per second. So when it hits the ground, that's what's going on. And that determines its likelihood of breaking or not. Okay. If it hits the ground at a slower velocity, probably has a greater chance of surviving. Mason's guitar, hopefully you watched the video. It did not. So that's at this point right here, and that would be the slope of the tangent at that point. Find and interpret the second derivative. So here's the first derivative. The second derivative, and this is really why Leibniz notation is the way it is. It's going to say d2h all over d2 squared, or dte squared, rather. So it's just going to be negative 10. But its units are going to be meters per second squared. And there's no t in there at all, so the acceleration, we know it's acceleration because of the unit, right? It's rate of change of velocity. It's rate of change of the rate of change, and meters per second squared is acceleration. The acceleration is always about 10 meters per second. And the negative part is kind of telling us that it's happening in a downward direction, or it's accelerating downward, or that velocity is always decreasing. And we'll get into some better definitions of those things very soon. Now, does that make sense? Well, if you know about the acceleration on planet Earth due to the force of gravity, then it's about 9.8 meters per second. This question is just taking that and using slightly nicer numbers, so it's not quite as accurate, but it's a little more digestible. Okay, but we could make it a little better by saying a different value right before that t squared, just slightly different. So there's meaning to each of these. The original function was height. The first derivative was height per time, or velocity. This is really velocity here. And the second derivative was acceleration. When does the guitar reach its maximum height? So we know that we've got this kind of equation. Let's go back to the graph, though. When it's at its maximum height here, what do we know about the slope of the tangent? Well, the slope of the tangent is going to be 0. Okay, right over here, the slope is positive, slope is positive. Here, the slope is negative, slope is negative. But right at the top, the slope is going to be 0. Or in other words, the velocity, just for an instant, is 0. Because the velocity will be positive as it's going up, and negative as it's going down. So just for an instant, its upward velocity is 0, and then, boom, it heads downward. That's probably the easiest way to find this vertex right here. Now, some people might remember completing the square or using negative b over 2a in a parabola, but I think this is pretty slick. So we don't really need this a whole lot. What we want to do is find where is the first derivative equal to 0. And the first derivative is negative 10t plus 9. And where's that 0? Well, we can just solve this out. We got 10t equals 9, or t equals 9/10, or 0.9 if you want. That is the time when it makes its maximum. Now you might look at this graph and say, hold on, if it hits the ground at 2 seconds, why isn't the top going to happen at 1 second? Well, that's because Mason's standing on a stage. He's not starting from ground level. The guitar's not starting from ground level. And this plus 2 sort of deals with that. So the top of this parabola is going to be closer to the instant that he lets it go than to the instant that it hits the ground. Last question. What's the maximum height of the guitar? So if you want to find a height, let's think about this. Would we sub into the first derivative, the second derivative, or the original? I think you want to sub into the one that says h equals. Okay? H is for height. You can think of this as a function if you want. So h at t is going to be negative 5t squared plus 9t plus 2. And we just need to sub in this time. So this is when it happens. How high up is it? Well, let's just see. We can work this through. That's going to be 0.9 squared is 0.81 times 5, negative 4.05, plus a 0.1 plus 2 would give us a height at 0.9 of 6.05 meters, or about 18 feet. That's pretty high. That's probably why it didn't survive. So to recap, the first derivative of height or position with respect to time is velocity. This is really a big idea. The second derivative of height or position with respect to time is acceleration. If you're watching this video from the IB Oxford textbook, these are the questions. And if you're doing it from another textbook, maybe look for some stuff that is on vertical motion. That really brings us to the end of this video, but I do want to show some TI-84 hacks that are possible here. So if you want to stick around for that, great. If not, I hope this has been helpful, and good luck with the material. Okay, if we do some stuff with the GDC or the TI-84 calculator, I'm using an emulator here. It looks a little bit different, but it's mostly the same. There's the original height function, and I can graph it. And maybe I want to change my window settings so that all I see is times from 0 to 2 seconds. And I probably don't need to see much in the way of negative y values. Maybe I'll look at negative 1. But there's a nice graph of what's going on with this function. Maybe I'll look at a little more x's just so this looks a little steeper. There we go. Okay. So right over here is when it hits the ground, okay, at x equals 2. And I can find that 0 pretty easily. And if I wanted to work out the height when time is 2, I just go second calc. I choose value, and I tell it x is 2. And it tells me, it says in blue there, y1 equals 0. Bam, we've got that answer. If I wanted the derivative when it hits the ground, or when t equals 2, I press second, calc, I still have all this fun stuff, and I go to dy by dx. And I still have to tell it the x value. If 2, I hit it equals. It'll look a little bit different on yours, but you can see it says negative 10.999998, so to 3 sig figs, negative 11. It struggles with the exact values because it's actually using secant slopes instead of tangent slopes, but they're close enough together that it's almost the same. Now, to find the second derivative can sometimes be a little bit tricky. So I'll show you one more hack here to get the function, or to get the calculator to actually graph a derivative. I'm going to go to regular window settings again. And I'm going to head into y equals. And I'm going to hit math. And I go down here and I choose n deriv. Okay. And I want the derivative with respect to x of negative 5x squared plus 9x. And this is really hacking the calculator here. And when it says at x equals what? I say at x equals x. And that will get it to graph the derivative for me. There in red is the derivative. Okay. So that is the function for the derivative of height, or a velocity function. And guess what? At x equals 0.9, the derivative is 0, which means that we have a velocity of 0, or we have a max on the blue one. If I wanted to get to graph the second derivative, well, that's a little bit trickier. I can go math, same trick, n deriv of, and I can go alpha trace. And I can tell it to grab whatever's in y2 and take its derivative. I could have done this with the last one too. Okay, and then I'll get it to graph that. And it's going to have a really hard time. For most of these questions, you'll be working analytically, so it probably won't be a big deal, but there may be times when this can help out. Okay, folks, I hope this has been helpful. Good luck with the material, and take care.